Solving applications using rational equations. We're going to take a look at problems involving motion. Problems dealing with distance, rate, or sometimes referred to as speed, and time are called motion problems. To translate them, we either use the basic motion formula, which is distance equals rate times time, or some variation derived from that formula. Let's take a look at this example. Alex can run 5 miles per hour on level ground on a still day. One windy day, in which the wind blew at a constant rate all day, he ran 11 miles on level ground with the wind. In the same amount of time, ran 4 miles on level ground against the wind. What is the speed of the wind? To help us organize this problem and the information, and eventually solving it, I have a table here. Because it is a distance problem, and distance is found by taking rate times time to give us distance, I have the following columns. In this problem, it talks about him running with the wind, which means his rate of travel, or his speed, is increased when he has the wind at his back. When he's running against the wind, that wind is acting as a drag and slowing him down. We see similar situations with airplanes that have tailwind. If the wind is in the direction of travel, it increases the overall speed. If it's against, it has a headwind, it's going to be a drag and slow the plane down. Traveling by some kind of watercraft with the current adds to the boat's speed in still water, and similarly when the boat goes against the current, that current will reduce the speed of the boat. So we have similar situation here with Alex running with the wind and against the wind. What we don't know in this problem is the speed of the wind, so this will be our unknown, and we'll let W stand for wind speed. In the first sentence, it tells us that he can run 5 miles per hour on level ground on a still day with no wind. The second sentence tells us on a windy day in which the wind blew at a constant rate all day, he ran 11 miles on level ground with the wind. That means that his ground speed was, when he's running in with the wind, that is enhancing his speed. He normally runs at 5, and with the wind at his back, it's increasing his speed. He ran for a distance of 11 miles, so we can put that under our distance column. It also tells us in the same amount of time, he ran 4 miles on level ground against the wind. So a distance of 4 miles against the wind, and what happens to his rate is his normal calm wind day, or no wind, is 5 miles per hour. When he's running against the wind, in other words, his return trip possibly is being slowed by the wind because he's encountering this headwind. We'll express that as W, or 5 minus W. How do we fill in time? Well, we have a formula of distance equals rate times time, and if we're solving for time, we will undo the multiplication by dividing by R. So we end up with time is found by taking distance divided by rate. So to fill in these two cells, we'll take the distance of 11 and divide it by the rate given as 5 plus W to fill in the with time. Similarly, we'll do the same thing for the against running information. The distance of 4 divided by the rate, which was 5 minus W. Now, we have our table filled in. How do we solve the problem? The problem tells us that in the same amount of time, this individual is running with the wind and against the wind. This is going to give us our basis for our formula. The time that he ran with the wind is equal to the time that he ran against the wind. Well, what was the time with the wind? It was 11 over 5 plus W. What was its time against? Well, we just found that, 4 over 5 minus W. We have a rational equation. We can, normally, we would multiply by the least common denominator, which is a 5 plus W and a 5 minus W. We can multiply both sides by that amount, but in this particular problem, since we have a fraction or a rational number equal to another rational number, we can actually solve this by using our cross multiplication. And the cross multiplication, if you have a rational number equal to another rational number, cross multiplication says that the product of the extremes equals the product of the means. This only works when we have a rational number equal to a rational number. If there was something else added on here, we would have to multiply by our least common denominator. But just as an alternative here, and perhaps a shortcut, we'll use our cross multiplication option. That means I'm going to take the numerator 11 times the denominator across from it and set it equal to this diagonal, 4 times 5 plus W. We've eliminated our fractions, or our rational expressions. Now it's a matter of simplifying our equation to solve for the solution. We need to use distributive property, 11 times 5, 55, 11 times W. On the right-hand side, 4 times 5, and 4 times W. We've eliminated the parentheses. There are no similar terms, anything to simplify on either side. Next, let's get the variable on one side and the constant on the other. So if we would add an 11W to both sides, we will have a 55 left on the left, a 20 plus 15W. Next, we want to get the variable by itself, so we'll subtract 20 from each side. 55 minus 20 leaves us with a 35 is equal to 15W. And the only thing left then is to undo multiplication with division. 35 divided by 15 is, if you use a calculator, 2.3 repeating. Fraction-wise, the repeating 0.33333 is 1/3. So 2 1/3, this is our wind speed. Depending on what version they want the answer in, whether it's rounded to the nearest tenth or whether it's a rational expression, either one of these is going to work. The speed given for Alex's running rate is 5 miles per hour, so this would be in miles per hour as well for the wind speed. And it's always a good idea to replace your variable with the value and verify that this is in fact the correct solution.